All right, so now let's go back to looping. I'll do looping, and next time we will do the extraction of the force. So how do you calculate the looping? The looping is also has to do with a time. I mean, it's not a time scale in the polymer mode. It is not contained really in this mode here. This is a mode of relaxation of the polymer. Looping is something else. So the looping time, which is really the mean first looping time. So this is the time it takes so we have bead R1, okay, Rn, and you're interested in when this bead is entering for the first time in a ball of radius epsilon of R1. So let's define tau. This is the first time that R epsilon or Rn t minus R1 t for a Ross polymer, this is less than epsilon. Condition that, of course, at time 0, R1 is the distance between R1 and Rn 0 is strictly less than epsilon. It's whatever it is. If, for example, it is given. You have a given length. So this is, now we're interested in calculating the mean. This is what we're interested in. Mean first looping time. How you calculate this time asymptotically. So R1, Rn are satisfying the Ross equation, which is minus the gradient phi. You take the gradient with respect to Rn plus square root of 2d and the noise. This is for all of them from, except the first and the last, from 2 to n minus, I mean for all of them actually,
David, can I just ask a question?
Yes.
Isn't another question that you're interested in the looping of a subloop in a very long chain?
Yes.
So I mean.
Yeah. So here I'm looking at the two ends. We can also,
I understand that.
you can also do it for the two in. That's right. You can have let's say A and B. And this is what you are anticipating. What is important is not the entire chain. This is the, let's call it N and M. So instead of having capital N in here, you have N minus M, absolute value. This is what you can show. Yes. And this is important. It doesn't matter what happened. Yeah.
Explain to me again the initial condition.
Initial condition, you have to be outside.
But if you're just outside, it won't take very long. If you're
no, but in average, if you average of a steady state distribution, let's suppose here you take time 0, you take a steady state distribution that in your sample of, I mean, realization that, you know, the probability they are inside at time 0 is small. So let's, for example, assume, you can assume, for example, that time 0, I don't know, Rn is equal to, what really we did here is we took steady state distribution at time 0, assuming that you're at steady state. Steady state is given, you have basically a Gaussian distribution for the position. All right, so this is the phi, this is the potential well that we have. This is R1, Rn, which is kappa divided by 2, the sum of Rk minus 1 squared from 1 to n minus to n. Okay, so now let's give an interpretation of this quantity. This is actually quite nice. We can rewrite this Rn using this. That is, you invert this matrix, and the condition is that it's going to be a condition on UP. So why is it interesting to go into this UP state? Because first of all, we separate U0, which is really translation, which has nothing to do with looping. Translation is just the motion. So this is out. Now suppose you move your camera with your polymer, so remove the translation. Now we are left only with rotation, which is U1, UN minus 1. And so now we are going to give a condition. We are going to work on the space U1, UN minus 1, which is the right space to work on. So now, what is U1? So the space, well, we are looking at the problem. So we take the entire monomers, the entire polymer, the joint, we're going to work on the joint probability distribution function of U1, UN minus 1. So for example, if you start in dimension 3, they're all in dimension 3. So you are, let's say, in the space R to dimension 3, n minus 1. And so you can rewrite this. You invert Rn as a function of UP. This is an orthogonal matrix. And now you will write this condition. And this can be rewritten the following way. 2 multiplied by square root of 2 divided by n. Sum for p odds of cosine pi p divided by 2n. This has to be less than epsilon. So this, again, you do the calculation, you find that there are cancellation. Now we are back to the Ross model. Ross beta equals to 2. So this is Ross, mean first passage time, for a Ross polymer. So this is the condition. So now let's understand what we are looking at. So now we have the space. You have all of your variable. And basically, you're done when you satisfy this condition, which is exactly rewritten this condition with this transformation. So let's write now the submanifold. This is U1, UN minus 1. Let's call omega tilde, this is omega tilde, is exactly R3 n minus 1. So such that you have this, so S0 is when you take this condition equals 0. So UP cosine P pi divided by 2n. This is exactly for P odd. This is exactly I've burned already 2 pieces of chalks. So, UP equals, what did I say? Yeah, 0. And so now you're interested in S epsilon. This is going to be, so in your space, there is a subdomain, which is really a plan here, because UP is like, let's imagine you have x1, xn. This is hyperplan. And S epsilon is what? Is the ensemble of points that are at a distance of S. So here there is a square root of 2 that I don't discuss. This comes from the normal, because of the norm of the normal to this hyperplan. So you're interested in what is the mean first passage time. So this is coming to a question where you start. Suppose you start outside, and we will see that there is a Gaussian distribution behind. So you start outside. You have basically, so you have your space. You are removing an ensemble. This is S epsilon. So let's say you start uniformly distributed outside. So we will average over the initial distribution. And so you have a dynamics, which is the dynamics of the U1, UN, which is all our Ochlen-Uhlenbeck. And so you move in your space, and you're interested, when are you going to hit this boundary for the first time? So it's a mean first passage time problem, but you're in very high dimension, r3 to the power n minus 1. Right, so let's write this down. And then let's write, then what is the mean first passage time to this? So now if you're interested, really, in the probability distribution function of the joint, which means u1, u2, un minus 1 times t. So this is the joint probability of all of the n minus 1 t. So this satisfies, so let's call this p, and I use the index t here. This is p, yeah, all right, pt of x, pt of u. So this satisfies, by definition, the Fokker-Planck equation, which is dp dt equals, so you have Laplacian, so there is, let me put here the diffusion coefficient equals 1, otherwise I have d here. D, so Laplacian p plus divergence of gradient phi multiplied by p. Phi is the potential which is defined here. And now, for example, so the initial condition, you can take whatever you want. It's a uniform distribution. You take P0. P0 of x can be specified later. P0 for the moment is a function. With the condition that absorbing boundary condition, P has to be equal to 0 on this boundary of S. So this is boundary of S. Right? So this is what we have to solve. This is an abstract problem. And now we would like to find how we, so let's from this see where the mean first passage time comes from. And then let's relate the mean first passage time to the eigenvalues of this operator. And then we're going to connect to the math theorem using the, what is the eigenvalue of this operator in the total space when you remove something. This is the connection with the spectral theory. When you remove, in the 70s and 80s, there was a lot of literature in mathematics starting by Mark Katz, where you looked at Brownian motion. So you start to remove an ensemble of sets in a domain, and then you look at when the particle is going to be absorbed. They started with a circle, and then they look at if you remove an ensemble of circles, and of course what is important is the distance between the disk that you are removing. Okay, so let's. So now, what is the solution of this equation, at least formally? This can be expanded in terms of eigenvalues and eigenfunction. So Px of t, if it's just, suppose this is 0, this is just like the Laplace operator. Now here you have to, it's a self-adjoint operator, so you can always remove this, or use the function transformation to have the exponential phi in the eigenfunction. So you have the sum of some coefficient, IA. This is the eigenfunctions, exponential minus lambda IT, exponential minus phi. Again, d diffusion coefficient here is equal to 1 to simplify. And you have to sum over I, so these are the eigenvalues and eigenfunctions. Okay, so what is now the probability, P of t, is the probability of a loop. So this is the probability of tau epsilon less than t, that is, now let's think, If tau epsilon is less than t, it means that you have formed a loop. At time t, you have already formed the loop. Here, at time t, you haven't formed the loop. Is this correct? Yeah, I don't know, it's not written. So let's think. This is a probability that you're still in the domain at time t. So this is integration over omega epsilon of the probability distribution function px of t dx. So omega epsilon is your space minus omega epsilon is omega tilde minus s epsilon. So if you integrate the probability distribution function over your space, you're still inside, so you haven't formed the loop. So this is correct. And so now the probability, so this, if you can take the solution here, you can integrate this from 0 to infinity. You take this over omega epsilon, and you get here a sum of whatever coefficient. This is not going to be a constant. This comes into here, and you get a sum of exponential ck exponential lambda kt. And so now, let's go back to the question. So we took for p of 0, exponential. So this is the distribution of the initial point that you asked. So this is exponential phi over omega. The volume here is the volume of the space with this weight function, exponential phi. So omega is integration of omega tilde exponential minus phi of x dx.
Hold on, don't you need to exclude the points that are inside the...
Yes, all right, this is true. But they are of size epsilon, basically. Yeah, okay. So let's call it omega epsilon here. Yeah? Okay. So now the mean first passage time, tau epsilon, is the sum of the integral of this. So this is Ca divided, so diffusion constant is equal to 1 lambda I epsilon. Well, lambda I, so let's call it lambda I for I equals 1 to infinity. Okay, so now, in principle, if you want to calculate mean first passage time, you need to know the spectrum, which is very demanding. So when we started to look at this using simulations, we could find that this probability distribution function of a loop is basically, you can take something of this form. At least you start with the two terms, lambda 1, lambda 2. This is normalized to 1. So this actually carry about 0.9. When n was, let's say n equals, you do simulations, you have, let's say, at least 30 to 64 beads. And this can carry some of it. But basically, the idea is that the process was almost Poissonian, because it takes a long time. It's a rare event. And basically, you don't care about the rest. Most of it is accounted by the first term, suggesting that the mean first passage time, when you calculate this, can be just given by the first eigenvalue. Now, okay, so I'll continue next week. Sorry, I didn't meant to take 10 more minutes. So I'll stop here, and the next week I want to go to this. So as Dan said, here we have excluded a region. So this is what? This is the eigenvalue of an operator where we have excluded a region. Now, how do you connect the eigenvalue of let's say, the operator where you have no, you haven't removed anything with this eigenvalue? So this has been done, and again, it follows the idea of marked cuts. There is a shift and the shift has been calculated. This is called the Chauvel and Feldman theory. I just write in here so that you may have a test to come in 2 weeks, not next week, in 2 weeks. The idea is that lambda I, for the entire spectrum, this is for the entire spectrum, is a shift compared to the, so let me, this is the spectrum eigenvalue of the operator which has no perturbation. This is a perturbed one. C2 epsilon integration over S eigenfunction squared for the associated eigenvalue here, integrated over S. So this is really the volume induced on your submanifold. So I don't know how to write this, but this is the dV on S.
So S is the part you removed?
Yeah, S is S0. Yes. So this is a normalized eigenfunction. So you see that it's of this order epsilon, and what is important here is where this epsilon comes from. So somebody asked at the beginning, yeah, I think it was Peter. If in dimension 3 it's 1 over epsilon, dimension 4 is 1 over epsilon squared, why we still get epsilon in high dimension? Here, what is important is that what you are removing here, this, how many equations do we have here? If you are in dimension 3, if UP is dimension 3, you have 3 equations. So you have 3 constraints. So if you are in n dimension, basically you are removing something of codimension 3. And this formula is exactly in this case. If you have only 2 constraints, if you are in dimension 2, instead of epsilon here, you get 1 divided by log of 1 over epsilon. Yeah. So this is where it comes from. In this formula, you are using the fact that it's codimension 3. And so it's epsilon, and this is epsilon. So as we're going to see next week, for the first, if you have an eigenvalue, the first eigenvalue of the Laplacian, if you have a boundary, periodic boundary condition, this is constant. So the eigenfunction is constant, and the eigenvalue is 0. So this is exactly 0. And what we need to calculate here is this integral over the path of the closed loop. And this is normalized, and normalized is the space basically of all the loops. This is what we need to calculate next week. The integral of this quantity, so it's going to be a constant, of this is dV associated to the exponential phi, so this is going to be Gaussian integrals. Because here this is, again, the Laplacian, it's not exactly the Laplacian here because we have the exponential phi. So the first eigenfunction is exponential phi. Exponential phi, this is the Gaussian. So this Gaussian integral, basically we have to integrate exponential phi over the entire space of all the polymer, and then the exponential phi over all the loops. And the rest of the geometry is taken care by epsilon, and C2 is, I will write down, this is associated to the gamma function. I mean, it's a given value square root of pi. So this is the structure of this, which is going to be exactly the first order term in the mean first passage time. That's the idea here. And in 2 weeks, we'll go step by step to calculate this term.
Wait, Dave, can you just clarify that integral there? That's over the excluded part? Or that's
This
over
is now an integral over, let's of the skeleton. There is no more epsilon here. So you have exactly the loop. It comes exactly, you have whatever it...
the boundary of the loop.
It's exactly the loop. You come back to epsilon equals 0. So you integrate over... Well, okay, let's write it. It's exponential minus phi, so you have to sum of ui squared, something like this, from y to n minus 1. So this is going to be the integral of du1, du n minus 1, but there is a constraint now. And the constraint is that the un minus 1, or depending on if it's odd or not, has to satisfy this. So you can express one of them in terms of the others, put that into integral, do the calculation of the Gaussian integral, and you get a formula. Next week we'll do this. This is you integrate over something of minus dimension. I mean, you have removed, actually, you have removed here. This one is going to be connected to the other one, so it will disappear. And so if you're in dimension 3, the uk or un has 3 coordinates. So you're removing 3 dimensions because you have 3 constraints here. So you plug back into that here. You express un minus 1 in terms of u1, un minus 2. And this is what you have to calculate. We'll do that next week. Sorry, I have been taking 15 minutes more. But I don't have my children today to pick up. That's why I didn't worry much about the time compared to the previous days. Thanks.